This is lecture 15, and we're going to start in this lecture to move from supervised learning to unsupervised learning. So at the beginning of this lecture, we're just going to talk real briefly about what unsupervised learning is. And so for the first half of our class, roughly speaking, we had a look at supervised problems. And generally speaking, what these problems are, these supervised problems, is some kind of prediction problem. Where the idea is we use covariates, our x's, to predict a response, call it y, right? And so you'd see this training data, and your goal was, your training x's and your training y's, and your goal was to build this function. Unsupervised learning isn't quite the same problem, and it's a little more nebulously defined. Basically, unsupervised learning is kind of finding / summarizing. I'm supposed to read summarizing patterns in the data. So the reason we called the first set of problems supervised problems is because we had training data to supervise or inform and estimate a f hat. So we had this training data, we had some truth, and we had some x's, and we had the true y associated with that. And basically, they kind of is a supervision where we give it to the algorithm, and we say, look, these are the x's, these are the corresponding y's. You know what's going on here. Learn the relationship. And so this is some of what was at one point, I guess, referred to as supervision. Unsupervised learning is we don't have, say, no distinct x's versus some y. There isn't one particular feature that we're trying to predict. All we have, in some sense, is our x's. We're not trying to predict some covariate from some other covariates. All we're trying to do is summarize the patterns, trying to refine the data in an interpretable probably how you spell that way, be it for humans to understand or for further algorithms to understand. So there are a couple different example unsupervised problems, and the first kind of two major classes we'll look at, and the kind of the focus of this lecture is dimensionality reduction. And the idea with dimensionality reduction is to basically represent the data using a smaller number of features. So we start off with some p covariates, and what we're going to do is we're going to use some unsupervised, that's not how you spell unsupervised learning to produce some fewer number q, much smaller than p features that approximately describe the data. So this is in some way related to variable selection, and hopefully sometime next lecture we'll talk about how sometimes these dimensionality reduction techniques can actually be used in a supervised context to produce some kind of quasi-variable selection. But dimensionality reduction is basically reducing the amount of features we have, but not losing too much about the data. The second kind of broad class of unsupervised techniques might be called clustering. And the idea with clustering is to basically group data into clusters. Let's say into similar, that's supposed to spell similar clusters. So the classic example with this, if I have two x's, right, there's no y's in this unsupervised learning. We just have some x's and we're trying to summarize the patterns. And so maybe my x's look something like this. This is a real classic picture. If I plot my two x's against each other, I get my points that look something like this. And to our eyes, it looks like there are two groups. It looks like there's some group 1, and there's some other set of points which we might call group 2. And so the unsupervised technique would be to learn these groups. And somehow we have summarized the data because we say in some way this data has this hierarchical structure where the data points belong to one of two groups. This is different than a classification problem. We don't actually, there is no correct answer here often. It's just, is it possible to get out some kind of group structure? We don't ever know if we're doing it right, because it's not like one of these points belong to two different classes necessarily. We don't know. Maybe they do, or maybe it's just some structure, some other kind of latent structure in the data. But we'd like to kind of learn these groups. Now, this is a very clear example, and it's obviously a more difficult problem than general when you have very complicated data. But somehow that grouping, or what's called clustering the data, is summarizing in a nice way some of the structure that we see in the data. And all we have is our x's, and all we're trying to do is say how are our data points kind of structured in the x space. There's nothing we're particularly trying to predict here. So today, and so next time, we're going to talk about principal components analysis. And principal components analysis, denoted PCA, has about 1,000 different names in various subfields. So engineers have called it maybe POD. There's various names depending on the subfield. Statisticians tend to call it principal components analysis. And it's going to be our first unsupervised technique. And it's a technique for dimensionality reduction. Let's say dimensional reduction. Principal components analysis is potentially one of the most useful things that we learn in this course. It is used absolutely everywhere, all the time. And many times people don't call it that, but it is what's happening. And we've actually basically already done a lot of the hard work for PCA. It's a very linear algebra intensive method, and so we'll see how this connects way back to our first lecture. But it's probably one of the most useful techniques in this entire course. So in the unsupervised setting, we have some data matrix X, and so X, we're going to say, is an n by p matrix. And you can either view, we talked about this is a little bit of a review of the first lecture, you can view this X in two ways. You can view it row-wise, where the rows are observations. So the first row is observation 1, the second row is observation 2, the third row is observation 3, etc., all the way down to observation capital N. Or you can alternatively view this column-wise, where the first column is variable 1, the second column is variable 2, etc. The last column is variable P. And this is useful to keep in mind both of these viewpoints. We can visualize this in a couple different ways. And one useful way of visualizing it is in what's called the feature space, or the variable space. So here, this is basically viewing it column-wise in some ways, or I guess in row-wise other ways, but it's basically viewing, we're thinking of a p-dimensional space. So maybe, let's say p is equal to 3. I would get a 3-dimensional space, and each of my coordinate axes would correspond to 3 variables, my x1, x2, and x3. And in this viewpoint, I'm going to have n points. My n rows are each vectors in this p-dimensional space. So here, x, we can view it as x1, x2, all the way down to x capital N, where the x little n is a vector in our p. It's in our feature space. And so these points live in this p-dimensional space here. So in some ways in this viewpoint, our data we can think of data as living in some p-dimensional space, each of the dimensions corresponding to one of the variables. And dimensionality reduction basically asks the question is, can I get away with fewer dimensions? So the simple case here, which we've talked about for the past couple lectures, let's say simple case, would just be some kind of variable selection. Now, we have to be careful. You can't really do a variable selection in the way we talked about it, because there is no y for unsupervised learning. There is only x. We only have the x's, and we're just trying to summarize them. So for variable selection, what you do is they retain variables, x's that are highly correlated, for example, with my y. But there is no y in this case. But nonetheless, you can think about, so here's my 3-dimensional space. Let's say, look something like that. And again, I have my points here. Just draw some example points. So these are my rows, these are my observations. And I could, for example, remove x1. So what would happen if I get rid of x1? It just gets rid of that coordinate. And so basically that's going to project all of these data points down onto the x2, x3 plane. So maybe if I project them down, I'm drawing little streamlines here. So basically here we've projected data onto x2 by x3 plane. So one thing you could do with variable selection, you could say if I just remove x1 from my data, maybe I don't lose much. So let's say maybe I don't lose much if I remove x1 from my data. And what I mean by remove much, we will talk about specifically, but the goal or the hope is that I have made my data simpler without losing much information. So that's the hope. Here's an even simpler example. Let's say simpler yet. Because it may seem, in this example, it seems like we might be losing a lot of information if we remove x1. What if I just have two variables, x1 and x2? And what if x1 is approximately equal to x2? Maybe not exactly, but my red points maybe very closely fall on some line here. So if I were to look at this, maybe this 45-degree line, basically what I've seen here is that the correlation between x1 and x2 is high, or i.e. x1 and x2 are redundant. And one thing I could do is I could just throw out x1 or x2. Alternatively, I could take this linear combination of them, I could summarize them down into this line, which is maybe 1/2 x1 plus x2. I could instead go from x1 and x2, and I could summarize down into one variable, which is kind of the 45-degree line there. And this starts to get closer to what Pca wants to do. Pca is basically going to find a way, well, let's just write it down. Let's say goals of Pca. And the first goal is to reduce the data, i.e., let's say number of variables in my data. This is also called the dimension of my data, right? If I remove x1, I've gone from a 3-dimensional data set to a 2-dimensional data set. And similarly, in this case, if I go from x1 and x2 to x1 1/2 x1 plus x2 as the average of them, I've gone from 2 variables to 1 variable. So I've reduced the amount of data. And the second goal here is to not lose too much information, whatever that means, or equivalently, to maximize the amount of information or interestingness in my data retained. And these are kind of flip sides of the same thing. If I reduce my data without losing a lot, if I minimize how much I lose, that's maximizing how much I retain. So let's just write that. Min lose is equivalent to maximizing how much I retain. So reducing the data, or the number of variables, the dimension of my data, seems pretty straightforward. Basically, I want to go from some original set, x1 to xp, some p variables, and I'm going to have some magical Pca process that is going to spit out some new set of variables. Let's call it z1 to zq, where q is much less than p, hopefully. So that seems pretty straightforward. If I can take my original set of variables and produce a new set of variables, and q is much less than p, that seems to make sense. The harder question is, what does it mean that these new set of variables either minimize how much information I lose or maximize how much information I retain. So the central dogma here for this is that variance in my data is interestingness or information. So variance in my data is going to be equivalent to information in my data, retained in my data, or the interestingness of my data. So when I want to minimize how much interestingness I lose, I want to minimize how much variance I lose. And I want to maximize how much information I retain. I want to maximize how much variance I retain. So does that central dogma make sense? In some sense, it does, because the only thing that's interesting ever about data is how it's different. For example, if I have two variables, x1 and x2, and my observations look something like this, right? I measure some feature on people, and one of the variables has differences, and the other variable is exactly the same. This other variable, x2, tells us basically nothing interesting. It's the same for everyone. So why do I even need that? It's just some value. Once you establish that value, it's really not that interesting. There's no differences among people. You know, if I want to study, you know, how, oh boy, what do I want to study? You know, something about the gene expressions of people. If one gene is always expressed the same in everyone, that gene's not really that interesting of a gene. It can't be driving any interesting behavior. It doesn't tell me anything different about anyone. On the other hand, this one tells us something about the data. And ultimately, our unsupervised techniques are just trying to summarize something about the data. The summary of x2 is just one number. What's that? What's the, you know, what's my level here, my mean level? But a mean level is not going to summarize everything about x1 because there's a lot of variation. And so PCA is going to try to create a new set of variables, x1 to xp, I'm sorry, from x1 to xp, it's going to do the z's, that somehow minimize the amount of variance lost. So it's going to combine the original set of x's into a new set of variables that loses as little information as possible. So how PCA operates, if we go back to our picture of our feature space here, what was it, x2, x3, something like that, and I have my coordinate points here, and my data looks like this, maybe, something like that, okay? The idea with PCA is that instead of just removing x2 or removing x3 or removing x1, what if instead, let's say, instead of removing a specific variable, or instead of maybe removing dimensions of our data aligned with the axes. So instead of removing x1 just because it happens to be aligned with the axis, or x2, let's reduce to any good subspace. So in some ways, say removing x1 is reducing us to the x2, x3 subspace. But a more interesting thing would be is what if I just, instead of taking a subspace, reducing down the dimension to a two-dimensional subspace aligned with the axes, I reduce down to a two-dimensional subspace, but it needs not be aligned with the axes. And so I'm going to instead project my data down onto this thing. So I'm going to project my data in whatever way it goes. So maybe some of these are above the plane, some of them are below the plane. And what I'm going to do is I'm going to project data onto this subspace. So this is similar to what we did above when we did this variable selection. We projected onto the x2, x3 subspace. But there's no particular reason we need to choose that subspace so that it's aligned with the axes of that space. We can choose some subspace that is not aligned with those axes. The idea with Pca is that maybe my data looks like some pancake in 3 space. So here is R3. My data technically lives in this three-dimensional space. I've measured 3 variables, but maybe it really looks like a pancake in 2 dimensions. But it's like a pancake living in this three-dimensional space. But do I really need 3 dimensions to represent my data? No, it's nominally 3-dimensional, but it's kind of this flat pancake of data in 2 dimensions. And so if I look at a subspace like that, and I project my data down onto the subspace, because it's basically already 2-dimensional, I'm not going to lose that much information by projecting down onto this 2-dimensional subspace. My data is basically already 2-dimensional. And what Pca will do is it will say, well, what if I just instead create a 2-dimensional subspace and I project my data down onto that, and I'll call the first dimension Pc1 and the second dimension of this subspace Pc2. And what I want to do is work with this, with these principal components instead. And that's the whole game. And that's exactly what Pca does. It says, I'm going to take my data. If it could be in high dimensions, but it's the easiest way to think of it is that it's technically nominally in 3 dimensions, but it kind of lies mostly in some 2-dimensional subspace. There's a little bit of perturbations out of that subspace, but basically it lives in that subspace. And so if we just actually take that subspace, we just project the data down into that subspace, I don't lose that much information. And I'll just instead reorient my data in terms of I'll remove x1, x2, and x3, right, which are my original axes, and I'll go to a new set of axes called Pc1 and Pc2. So let me just summarize this real quick. So what Pca is going to do is take original x1 to xp and summarize or create my smaller set of variables z1 to zq. And indeed, what's going to happen, because we're working really nicely with linear spaces, these z's, if my coordinates here, let's say w1 is one basis vector of the subspace and w2 is the second basis vector. So let's say if the w, let's say, what do we want to call it? I is the ith basis vector for this subspace, then we get a really simple relationship where if I look at the coordinate in this new subspace according to my bases, what do you do if you have your original matrix X, right? And so let's say X is my n by p matrix. And I want to use this somehow to create a new Z matrix, which is going to be n by q. So it's going to have q columns instead of p columns. How do I translate, how do I project down that data onto a new subspace spanned by basis vectors, these W's? All we do is we're going to right multiply by W. If W is my matrix with these basis vectors, W1 as the first column, W2 as the second column, all the way up to WQ as the last column. Alternatively, one can think of the ith principal component, so these, let's say the Zi is called the ith principal component. Let me just bring this down here. Zi is going to be X times Wi, which is just a linear combination of the columns of X. So it's like Wi1 times X1 plus Wi2 by X2 plus dot 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 plus Wi P by XP. So the Zi's turns out are linear combinations of the original variables, because we're working with it, we're just projecting them down to a linear subspace, and linear algebra says that if I want to get the Zi's, basically, which are kind of the coordinates, so this is basically Z1, which is my first component, and Z2, which here would be my second component. So each point here is going to be in this case, a 2-component vector. If I want to get those coordinates in my new subspace, according to my new basis vectors in that subspace, all I'm going to, I just multiply by the change of basis. This is the change of basis, matrix, right, from linear algebra, and that will convert my x's into z's in this new subbasis that spans my subspace. And so we can think of this as alternative. This gives kind of an alternative formulation. And there are about 100 alternative formulations for PCA, but an alternative formulation is that my Zi's are linear combinations of my x1 to xp, my original set of variables. And the kind of second thing we wanted to do with PCA, if we go back up to it, so first was reduce this data. And the way we reduce the data is we project down onto a subspace. And the second goal of PCA was to do this in a way that we minimize how much information we lose or maximize how much information we retain. And so you can formulate it a couple different ways. If we want to formulate it in terms of maximizing the information we retain, the formulation of PCA we're going to talk about is that the Zi's are a linear combination of my x's, where Z1 maximizes variance. So Z1 is going to have the maximum of the variance it can have. It's going to try to maximize how much variance is in that first coordinate direction, which is kind of this direction here. And, so if we believe the central dogma of PCA, which is variance is interestingness, then say Z1 maximizes the variance, right? We're trying to maximize how much information we have. Z2 will also maximize the variance, right? We're just going to pick our Z's to maximize the variance. So we can say for Z1, we're just going to pick the linear combination of my X's that maximizes the variance. You could say the same thing with Z2, but we don't want information to overlap between Z1 and Z2. So we're going to put the constraint such that the, say, correlation between Z1 and Z2 is 0, meaning they don't share any information. Z3 is going to maximize the variance. It's going to be the linear combination of my X's that maximizes the variance such that it is uncorrelated with not only Z1, but also Z2. And so forth, all the way down to ZQ. ZQ, we're going to choose as the linear combination of my X's that maximizes the variance such that it is uncorrelated with the rest. So kind of our principal components, one way that we can formulate them is we're going to look at linear combinations of our X's. We're going to try to maximize the variance of those linear combinations to maximize how much of the interesting information is that we capture in those principal components. But we're going to do that in a way such that the information of the various components don't overlap. We want to parsimoniously reduce the data as much as possible. If we have overlapping information between our variables, we haven't kind of reduced the dimension as much as we possibly can. So we're not only going to try to have them maximize variance, but we're going to try to have them so that they don't capture any of the same variability. So this is the formulation of PCA we're going to work with. There are a million other formulations, but this is kind of the maximizing variance formulation. They're all equivalent formulations, but you'll see this presented in other ways. So looking at linear combinations of my X's is equivalent, that maximize variance is equivalent to finding the subspace, which is just going to be linear combinations of my data, because linear algebra is nice to us, that minimizes how much information we lose. So finding the subspace that when we project our data down onto it minimizes the amount of information we lose is the same thing as finding these W's, these coordinate directions, so that when I project my data down to that basis, it maximizes the variability captured. So minimizing variance, or minimizing error, and maximizing variance are kind of flip sides of the same coin here. So let's look at the mathematics of this, now that we've kind of set up what we want to do. So just as mathematically, how we're going to formulate PCA is we have X, which is n by P, and we want to find a matrix W, which has columns W1 to WQ, so that if I look at, let's say, the variance, we could probably write this as one thing. Let's say, so that WQ, or let's say WI, let's write it this way, so that we maximize the variance of ZI, where ZI is X by WI. So basically we're looking at the ZI as linear combinations of my X's. And we want to maximize this variance subject to the constraint that the correlation between zi and zj is 0 for all j less than I. So for any of the preceding ones, that the prints of the zi's, which are our principal components, called the PCs, these w's, wi are called the weights. We want to maximize the variance of these principal components. Let's say that's the zi is the ith principal component. We're going to maximize this subject to the fact that it doesn't capture information that's already captured by the preceding principal components, which is captured by this correlation constraint. And we're going to add on one more constraint, which is that w is orthogonal, or equivalently, that the w sub i's are unit vectors. So why do we insist that the weights are unit vectors? If we allow the weights to be arbitrary vectors, we could always scale them and arbitrarily inflate the variance. So we need a little bit of constraint there, otherwise there is no w that would maximize it. We could always multiply by 10 and get it, and the variance would go up by a factor of 100, and you could always just keep increasing the size of the vector. So you need some constraint on the size of that vector. But that's purely kind of an optimization problem, because if you allow these things to be kind of unconstrained, then you could just inflate the variance, and it's not really that interesting. So it's not like we're avoiding anything too interesting. Okay, but the point is we want to maximize the variance of these zi's, and here we're talking about kind of sample variance of these zi's, subject to the fact that of this correlation constraint here. So let's take a second here. The proof of actually how to get these is not too bad if you build up the right machinery. So we're going to spend a little bit of time building up the machinery, and then the kind of punchline will come real quick from that. Okay, so we did a little bit of review at the beginning of the class, but I think it's worth going over some of this. So just let's just review some concepts in terms of vectors. So if x, is some variable, let's say x1 to xn, so basically some variable or column of x of our big matrix. We're just going to call generically the x, doesn't really matter, right? X bar, which is the mean, right, of, let's say, of this. Let's say little n goes 1 to capital N of my x sub n. One can write this as 1 over n times 1 transpose x, or 1 over n times x transpose 1, where 1 is a matrix of 1s. So, right, if I take the inner product between a vector of all 1s, and a vector, it's just going to sum up all the elements. And so if I look at 1 over n, that gives me what we call x bar. So this is just some cute vector notation. Kind of without lots of generality, we're going to assume x bar is 0. If not, we'll center our data. So typically PCA assumes that the data has been mean centered. So let's say PCA assumes mean centered data. Honestly, not a huge deal, but the classic conception of PCA, you assume things are mean centered. If we look at the variance of a variable, right, this has this formula. It's something like 1 over n, or 1 over n minus 1, doesn't really matter. Sum n goes this, of xn minus x bar squared. Of course, if x bar is 0, this just looks like 1 over n, the sum of the little xn squared. And we have a name for the sum of little xn squared. That would be the norm. squared. Or, equivalently, it's 1 over n times the inner product of x with itself. So if we centered our data, if x bar is 0, then norm squared is basically the variance of a variable. Cool. If y is another variable, some other column, whatever, and y bar is 0, then the covariance between x and y is just 1 over n times the sum of the xn, yn. All right, normally for covariance, you'd center them, you'd subtract off x bar and y bar, but if x bar and y bar is 0, we can ignore that. And so that's basically 1 over n by the inner product between x and y. So here, if x bar and y bar are 0, my data has been centered, then covariance, or let's say inner product, approximately is covariance. Or correlation. So what we've done is that you can think of, if your data centered, the norm, the square of the norm, being basically variance, and the inner product being basically covariance. So if x transpose y is 0, then our covariance between x and y is 0. And that's, say, if and only if statement. If and only if the correlation between x and y is 0. So in this nice centered space, norm squared is variance, and inner product tells us about correlation. So if we go back up to our problem, how we had mathematized the PCA problem, we were looking at the variance of something, which is basically the norm squared, and the correlation, which is basically the inner product between things. And so we can actually formulate this even more simply mathematically by using that kind of notation. If we have centered things in advance, we can make this kind of all a problem in terms of vectors. So let's rewrite this in terms of this new notation we have. So let's say we can just kind of simplify PCA by saying that what ultimately we want is our weight vectors. I mean, we can use those weights to define the zi's. We're going to get wi is going to be the vector that maximizes this, right? And this is basically the variance of xw, or the variance of z. So let's say xwi, or variance of zi, right? Where zi is our principal component, which is just a linear combination of the columns over x's, which is x by wi. So we can write our PCA problem as choosing w, let's say w1 is going to be the value, the weight vector w, such that when I use it and take the linear combination of x's according to that weight vector, I maximize this variance. However, we said we had this constraint that w, our weight vector, was a unit vector. Otherwise, if we just multiply w by 10, we'll just arbitrarily be able to scale that variance. So this is our first weight vector, w1, satisfies that constraint. Our second weight vector, which defines our second principal component, is going to be a similar thing, where you're going to maximize this variance of a linear combination of the columns of x. Not only, though, does the weight for this weight vector have to be a unit vector, it has to be orthogonal, or it has to be uncorrelated, right? We said it's uncorrelated with Z1, for example. So we said that the correlation between things, it doesn't capture anything associated with Z1. And so we could write that here. We would add on not only maxing over the constraint that the norm is 1, but that W, the inner product between W and W1 that we found first, has to be 0. That is saying the same thing as that the correlation there has to be 0. We can play a similar kind of game. W3, my weight vector for my third principal component, is again, I'm going to try and maximize this variance, subject to that the weight vector is a unit vector, the weight vector is orthogonal to the first weight vector, and it's orthogonal to the second weight vector, which means we'll see, we'll revisit that orthogonality constraint at the end, but we'll see that that basically ensures that that the principal components are uncorrelated. And we can play this game all the way up to WQ is, etc. Similar kind of deal. Maximize the variance subject to the fact that the weight vector is a unit vector, and it's orthogonal to all the previous ones. So that's the game, and it's just this maximization game. And so to solve this maximization problem, we basically have to look at maximizing, at how to solve this maximization problem. So let's do a real quick aside here. We'll see how quick we can make this here. But once I show you this aside, the proof is going to be really simple for figuring out what the answer is. So I just want to point out that that generally we can reparameterize maximization problems. So if A is an invertible matrix, and we could solve a problem, say, get X star as the argmax over X in some set S, let's say, of Fx, right? So this would be a kind of classic maximization problem. And you could alternatively look at the problem where Y star argmax over, instead of Fx, let's say F of AX, right? So you could throw this A in there like that. And here, let's say, instead of AX, let's just say AY, and we're going to be optimizing over some set. But basically what's going on here is you have original set S, and your little x lives in there. And you could, under your mapping A, send it to some other set. And it is, so under our mapping, we'd send x into this other set. And if we want to get the same answer, or we want to kind of solve the same optimization problem, somehow this A is just a reparameterization of the space. It's an invertible matrix. And so A defines a one-to-one function between here. So if I send x into some y, there's A inverse will take me from y back to x. And so we're basically going to get the same thing if I maximize where y is in, I'll say, A inverse of S, where I'm just going to basically apply A inverse to each of the elements of S. And if I solve this problem, what you find is that X star can be found. So maybe this is the original problem I want to solve, but for some reason I want to throw an a in here, is that x star is going to be a times y star. So this a inverse here isn't super important, but basically if I throw in an a here, I can similarly get back x star by throwing in an a here. So I'll let you think about why that's true. But basically all a is doing is it's a one-to-one function. It's just reorganizing, reparameterizing the space of things this set S over things over which I maximize. And so, for example, if say U is an orthogonal matrix, and I want to say maximize, let's say I want to solve the problem of arg max over some vector z that has, that is constrained to be a unit vector, and I want to maximize some function f of z. This is equivalent, since U inverse is U transpose, to saying this is U transpose by argmax over U transpose z is equal to 1 times f of uz. So I'm allowed to put this u in my optimization. I have to multiply by the inverse, though, out here. This is, as long as u, or before we had a, is invertible, we're allowed to do this. Or alternatively, another example, if I want to maximize over z, where there's a constraint that z is orthogonal to a, so z transpose a is 0, and I want to maximize f of z, I can equivalently, let's say I could throw my U transpose out front, right, which is basically this a here, and arg max of, and then I replace z with what we had here, which is basically the inverse. So I'd say z transpose U transpose a is 0, and I could put my u in there. So there's some tricks we can play, and I'm going to play one of those tricks. So that's a real quick overview, but you can think about why those comments are true. So let's go back to our PCA problem. The first problem we want to solve is this problem here, right? So what we want to solve is W1 is argmax over all unit vectors W, and we're going to maximize xw norm squared. Let x have a singular value decomposition, u d v transpose, then this thing can be written as the norm of u d v transpose w squared. And I can ignore this u because the norm of u times any vector a is just the norm of a vector a, right? And we proved this previously. Multiplication by an orthogonal vector does not change the length of a vector. So I can actually ignore that u. And I'll just get dv transpose w squared. And now I'm going to use this conversation here to do a little trick. I'm going to insert a v in here, but it means I'm going to have to multiply correspondingly. If I multiply by a v transpose there, I can multiply by a v transpose here, and I can add a v in here. Why am I allowed to do that? all V is doing is this is just a reparameterization of the solution. So my point here is that if I look at an invertible matrix, which is all it is a reparameterization of the space. And so it will just reparameterize my solution. If I add an A into my objective function, all I need to do to account for that is to add an A, reparameterize my solution in a kind of similar way. And so that's all I'm doing. I'm reparameterizing the space we're searching over by multiplying by V transpose, or I'm reparameterizing my, because V is orthogonal, it's invertible, I can basically add that V in there as long as I do the opposite out here. Now, again, V is orthogonal doesn't change the length of W, so this becomes V transpose argmax over norm W is 1, and the reason why is V is orthogonal doesn't change the length of W. And now I get some nice cancellation because V transpose is the inverse of V, so I just get WV, or dW squared. Now D is this diagonal matrix, which is super simple, so this whole thing, remember that D is a diagonal matrix with singular values down the main diagonal. So it looks something like this. It's kind of what my matrix looks like. And so when I multiply by W, all I'm going to get is the first element of W, let's say W1 times sigma 1 plus W2 times sigma 2 plus dot 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 W, let's say W R component by sigma R. And I'll get this whole thing squared because it's the norm of this thing squared. And I want to maximize this. Well, this is a really easy thing to maximize. So the way that we can maximize it, right, if you remember that sigma 1 is bigger than or equal to sigma 2 is bigger than or equal to sigma 3, right? These sigmas are ordered. So how do I maximize this? I'm allowed to choose my W's however I want, subject to the fact that they have to kind of, the sum of the square of them has to be 1. They have to be part of a unit vector. So what if I set W, if I want to maximize this, sigma 1 is largest, sigma 2 is the second largest. What if I just set W1 to be 1 and W others, let's say others is 0. So I set this one to 1, and I set the other 0, so they go away. That's going to be the largest I can get this thing, because it's kind of maximizing the coefficient on sigma 1. And so my solution is going to be V transpose times this vector with 1 in the first component and zeros everywhere else, which is just the first component, or first column of V. So first column of V. So it turns out that this first weight is just the first column of the V matrix from my singular value decomposition. So let's say this was PC1. But I can play the same game with other things. PC2, so W2, was argmax over all unit vectors W, and we're looking at the norm of xw squared, which is basically our variance. But we had another constraint that W1 transpose W is 0. And I can play a similar game well, let's do this one out. I can play a similar game where I can, let's just write it out. That's 0. If X has singular value decomposition UdV transpose to W, something like that, I can ignore that U, and I can multiply by a V in here, and get rid of it, so it just becomes dw squared, the norm of dw squared. Again, I have the condition that norm of w is 1, but I also need to multiply here by v, so this becomes w1 whoops, there should be a v transpose out front, so, right, so I get similar argument, I get that v transpose out there, and my w, how does this work out? It becomes w1 transpose v, or w1 is v1, right? So I guess I could replace this with v1, right? We know what w1 is. It's v1. And I get v1 transpose v transpose w. That whole thing has to be 0. And what this works out to be is that we can look at this constraint, v1 transpose v, I guess it'd be something like that, times my w. It doesn't really matter, does it? It is going to, the inner product between these is just going to be, this is going to simplify to the constraint that the first component of this w is 0. So how does that work out? It works out because, how does this work, right? So we want v1 transpose w to be 0, but then I can add in a v in this formula, right? And so I had to add a v transpose out front, and I'll need to add a v transpose here, and I have to add one here, so maybe there. So v1 transpose v transpose basically is going to be an identity matrix, or it's going to be a vector of, let's say, zeros. It's going to have a 1 up here and a bunch of zeros, and we're looking at the, so we'll look at the inner product of that with w has to be 0, which basically is going to say that this first component of w has to be 0, because the inner product between w and that thing has to be 0. And so we get a similar game here, where we solve this similar kind of optimization problem. But now w1 has to be 0, and so the next optimal thing to do is inflate the coefficient associated with w2 as much as possible. So I maximize sigma 2. And what that will give me is that my solution here is going to be like 0, 1, 0s, right? And so this is the second column of V, etc. So you can keep playing this game. And what we find is that our whole W matrix, which is n by q, is just the first q columns of my B matrix, where my X matrix has the SVD UDV transpose. So it turns out the whole punchline here, and then you can tell it's a little bit complicated of an optimization argument, but they kind of gave you the broad strokes of what's going on here, is that ultimately what we wanted to find is this weight matrix way back up here. For PCA, we wanted to find these W's so that I can convert my X's into the Z's by taking linear combinations, right? According to this formula, where Z is just X by W, right? These W's are kind of the basis of that space, where they project X down into that space. It turns out this W matrix is just, you get that if you do the SVD and you pull off the first columns of that B matrix. So the punchline here is that the procedure for PCA, which is that I'm going to convert my original x's into a new set of z's, is that one, we had to mean center columns of x, right? We derived all this assuming x bar was 0 for each of the columns. 2, let's say, call it x, maybe c for x-centered. Let xc have a singular value decomposition, u dv transpose. Then w is the first q columns of v, or q rows of v transpose. So I would denote that as v1 to q. And 4, my ultimate z's, which now is a n by q matrix, is x by w, or x by the first q columns, which you can see by the dimensions will give me a n by q matrix. So ultimately, PCA is basically a rebranding of the singular value decomposition. And the SVD, or PCA, whichever way you want to think about it, is basically going to allow us to compress our variables by looking at linear combinations of them into a smaller set of variables in a way that may maximize the amount of variance we retain or minimizes kind of the error we get when we reduce our variables in this way. So we're kind of at time, so we'll stop here and we'll look at how to do this in the lab, and we'll pick up here next time and relate this back to our variable selection and regression conversations we had last time.